So let us start with what is indexing and indexing mechanism. Indexing in reference to motion is moving or rotating a body to some other position very precisely. So a definition that we can give to indexing is positioning a workpiece at a precise angle or interval of rotation for machining operation is called index. And the definition of indexing mechanisms is given mechanisms for intermittent motion and force transmission termed as indexing mechanisms. So here what is meant by intermittent motion? Intermittent motion means the motion which occurs in regular intervals of time. That means the motion will not be continuous and steady. So such motions are termed as indexing mechanisms, and the process that positioning is called indexing. So these are the different types of indexing mechanisms we are going to discuss in this video: Geneva mechanism, Rachet-Paul mechanism, and worm wheel mechanism. So first, going to Geneva mechanism. See, you can see a image here. This Geneva mechanism is a mechanism in which rotation is transmitted between two links. First link is this link A, which is black color one, and the second one is link B, which is a green color one. So here you can see there are 4 slots in link B. Link A is called the driver, that is a black link, and link B is called a driven link because link A drives the link B. And in this mechanism, the important part is these slots. These slots helps us in rotating link B in regular intervals of time in certain degrees of rotation. The number of slots decide the degrees of rotation for each rotation of drive wheel. So the other thing here is the pink thing, that is locking plate. You can observe that a pin on link A enters the slot tangentially and leave out tangentially, and the other thing is link B rotates only when the pin is in contact with link B. So the other time the pink plate locks link B without rotating. So that is why this pink color is called locking plate, because it took the motion in a time other than indexing period. So let us know the working of Geneva mechanism. Here you can see a 6-slotted Geneva mechanism. On seeing the picture itself, we can say that the number of slots decide the number of degrees driven wheel rotate for one rotation of the drive wheel. So if the driven wheel has n slots, 360 by n degrees will be advanced for full rotation of the drive wheel. So next, let us go to Rachet-Paul mechanism. Rachet-Paul mechanism is a wheel provided with suitably shaped teeth, receiving an intermittent circular motion from an oscillating or reciprocating member called ratchet wheel. So this is a ratchet wheel, and here it is driven by a oscillating arm, and this oscillating arm have a pawl here. You can see this C and D are pawls. They are called pawls, and with the help of this C pawl, the oscillating arm gives intermittent circular motion to this ratchet wheel. That means ratchet wheel rotates in regular intervals of time but not continuously or steadily. And this D pawl is used to prevent backward motion of the wheel. Let us see how this is done. So in this mechanism you can see there is a oscillating arm. There are 2 pawls. Here the ratchet wheel has intermittent motion. That means it doesn't rotate continuously but rotates in regular intervals of time. So that is the characteristic of indexing mechanism. The way it works is this oscillating arm will be oscillating with some omega, and this pawl will push the ratchet wheel to move anti-clockwise, and this locking pawl will help in preventing from rotating backwards. And in order to change the speed or the angular velocity of this ratchet wheel, we need to change the shape of the spikes, that is called the pitch of the teeth, and we use springs in order to make sure that pawls are in contact with the ratchet wheel. So this ratchet wheel mechanism is mostly used in purposes where we need to block the backward motion. And the third one is worm wheel mechanism, also called a simple indexing mechanism. This mechanism is vastly used, and the name itself suggests that it consists of worm wheel as a main part. So it is mainly used in indexing rotating shafts or rotating some other materials for machining process. This worm wheel mechanism is widely used in milling process. So let's take milling as an example and go deep into the indexing of the worm wheel mechanism. So you can see a milling machine here, and the most important part here is the dividing head. And next we can see here a person fixing the shaft for the milling machine. This is the way we set up the milling machine. So next we set up a blade or a cutter which is suitable for the cut we need or the material of the workpiece we take, and it also depends on the shape of the cut we require. And then a support for the milling machine is fixed here, and then it is locked so that it has very less vibrations. And now you can see the first cut is being done throughout the workpiece, and then after making the first cut we need to make the second cut. This is where we need to rotate the job or the workpiece. Then you can see the person here using the dividing head in order to rotate the check of the dividing head and making the workpiece rotate to a certain angle which he requires to make the second cut. So here the dividing head plays an important role. Let us know how the dividing head works. In dividing head we have gear reduction and dividing plates mechanism. Here you can see many parts in a dividing head. The main parts are A. Crank, B. Index or hole plate, C. Sector arm, D. Chuck. And this dividing head is at the position of head in the milling machine, and this is the tool which we use to divide the circumference of the job or the working piece into the number of required equal parts. So these are the types of indexing: direct indexing, differential indexing, angular indexing. So let's come into direct indexing. In direct indexing we have the holes that are on the spindle of the head. So it has 24 holes. To better understanding, let's see that picture. Here you can see the holes which are attached. The whole plate is attached to the spindle itself. So near the spindle you can see a plate with holes of 24 in number. So these holes can be used in order to rotate the job or workpiece to certain angles. Like, let us take an example. You need a gear of 12 and the number of holes on the plate are 24. Then the number of holes to be skipped for each tooth cutting is, the formula is number of holes on the plate divided by number of teeth. Obviously in our case it is 2. So for getting a gear of teeth 12 we need to skip 2 holes at a time for every successive cut. But with this mechanism we can only make 4, 6, 8, 12 and 24 teeth gears, isn't it? Then how to make 15 tooth gear and how to make 120 tooth gear? So that is where the important indexing mechanism, that is the differential indexing mechanism, comes into play. You can see a whole plate that is attached to the side of the dividing head. This is the indexing mechanism and it is inbuilt inside the frame also. Let us see. So differential indexing mechanism. Differential indexing mechanism has a worm gear mechanism and the reduction rate of the gears is 40:1. This is the CAD model of dividing head we are talking about. The different parts of dividing head are crank, indexing plate, the sector arms. There are 2 sector arms here and then a frame that covers the indexing mechanism. So in order to have a good look at the mechanism, let us just suppress the frame. So this is the differential indexing mechanism we are talking about. You can clearly see that it is a worm gear mechanism here. The main purpose of using the worm gear mechanism is that it helps in having a good gear reduction ratio. That means we can divide the one rotation of the spindle into several rotations of the crank. Generally we use 40:1 gear ratio. That means 40 complete rotations of the crank results in only one rotation of the shaft or check or the workpiece. So these are the number of holes in each circle. These holes help us in further dividing one rotation of the crank into fraction of rotation. For that we use these sector arms. So let us take an example to make it clear why we use this index plate and the sector arms. The example is, we need to make a gear of 35 number tooth. For that we already know that the gear ratio of the dividing head is 40:1. So one rotation will be equal to 40 rotations of the crank. But we need to divide the circumference of the workpiece by 35 parts. So on dividing by 35 on both sides, we make that 1/35th part or the 1/35th division of the circumference of workpiece will be equal to 1/7th rotation of the crank. So when we rotate the crank 1/7 times, we will get the next position of the successive cuts. So every time we need to rotate the spindle for the next cut, we need to rotate the crank by 1/7 rotations. So we got a fraction of number of rotations of the crank. Then how do we do this? First we need to select the whole layer or the circle of holes which we should use. So These are the different number of holes or the different hole circles that are present on the index plate in our example, and these are the possible fraction of rotations that each hole plate give. Using 63, these fraction of rotations of the crank are possible, and so on for every circle of holes. But in this question, we need a fraction of rotation of 1 by 7th fraction. So we have two options here. We can either use 1 by 7 here, that is 63, and 1 by 7 here, that is 46. But for instance, let us use 63. For making 1 by 7th rotation of the crank, we need to skip some holes. The number of holes to be skipped is 1 by 7th part of 63 holes, that is 9 holes. So for every 9 holes, that will be 1 by 7th rotation of the crank. How do you make 1 by 7th rotation? That is done by using sector arm. So now we need to use the sector arms for easy indexing. Set both the sector arms at a gap of required fraction of required rotations. Here in this case we need 9 holes to be skipped on the outer hole circle. So here let us count the 9 holes: 1, 2, 3, 4, 5, 6, 7, 8 and 9. So let us move this sector arm here. So this angle or this proportion of the index plate says that it is the 1 by 7th rotation of the crank. Now just tighten this nut in order to make the both sector arms move together. So you can see on the screen that we can just move the sector arms together in this way, and we have fixed the sector arms such that the part between them is 1 by 7th rotation of the crank. Now let us make 1 by 7th rotation of the crank. Let us think the first position of crank is in this position, so we make the first cut, and then how to rotate the spindle to the position of second cut. So let's see that. First place these sector arms, one of the sector arm in coincident with the crank. Now we need to make 1 by 7th rotation, so make one whole rotation once and then 1 by 7th rotation again. So this gives the position of the spindle rotated to the second position where the second cut should be made, and then we perform the second cut. Now we need to rotate the spindle to the third position. In the same way, rotate the spindle to the coincident with the crank, and then rotate the crank one total rotation and then 1 by 7th rotation. Now we can make the third cut on the gear. This position is the position where we make the third cut. Now after making third cut to the fourth cut, we repeat the same process, making the sector arm in coincident with the crank and then rotating the crank one whole rotation and then 1 by 7th rotation. So this gives the position of the fourth cut. In this way we go on making the cuts until the spindle completes one complete rotation or the crank completes 40 rotations. So this is the use of the sector arms and the whole plate in indexing. So I think you got a clear idea about differential indexing. Let's move on to the next topic, angular indexing. So the third type of indexing is angular indexing. Angular indexing is nothing new. It is just an addition to differential indexing. Like in angular indexing, you first need to know how many degrees the spindle turns with one turn of the handle. That means if you turn one turn of the crank, how many degrees does the spindle rotate? One rotation of handle is equal to how many degrees of spindle rotate. In this case, as the gear reduction ratio is 40:1, by simple calculation, we can say that the spindle rotates 9 degrees when you rotate the handle once. So, where can we use this? Let us take an example for better understanding. See, here we want to make an uneven gear where the angle between two successive cuts is 22 degrees and other two successive cuts is 32 degrees. This cannot be made by uniform indexing, so we need to use angular indexing here. As we know 22 degrees, we know that for one rotation of the crank, 9 degrees of the spindle rotates. Using n by 9 as a formula, and we need to rotate 22 degrees, 22 by 9, that is equal to 2 4 by 9 rotations. That means we need 22 degrees and one rotation gives 9 degrees. Then how many rotations to get 20 degrees? That simple it is. So we find the number of rotations of the crank to be made in this case. So in 22 degrees case, that is 2 4 by 9, and 32 degrees case it is 3 5 by 9. So after knowing the number of rotations of the crank, although it is a mixed fractions, I think we know how to rotate in fraction of rotations by using differential indexing. So then that is very simple. Using differential indexing we can do the job. That simple is angular indexing. Angular indexing helps us when we know the angle between the two successive cuts to be made. We